Good evening, everyone. I'll be the MC tonight, James Cheesewright. Welcome to CIBSE Victoria's webinar tonight on batteries and power grids, presented by Jip Brouwer from, I'm going to say, Penske MTU Rolls-Royce. I think that's right, Jip.
Yeah.
With the rise of renewables in energy landscape and energy storage is required to manage the stability of our electrical systems. Lithium-ion batteries in particular are one on the rise in Australia. This seminar will discuss how and why and what benefits do batteries bring and what new developments are on the horizon. Tonight, as I said, we welcome Jip from Penske Australia. He has worked internationally in research, product development, and the development of batteries and microgrid projects. This presentation will be followed by an interactive Q&A, which I encourage you to ask questions because that's how you get the best out of these seminars. I'd like to move to the next slide, Jip. I would like to acknowledge the traditional custodians of the land on which we meet and pay our respects to their elders, past and present. The next thing is hours of free CPD. Tap into the hours of free content from around the region and the world within CIBSE ANZ webinars. This on-demand library covers a wide range of building services, engineering expert guidance to satisfy your thirst for knowledge. These are available through cibse.org.au. And then get involved. Join our chapter committee. We're always on the lookout for new talent. Oops. I'll just silence my phone. We're always on the lookout for new talent. Get involved in the chapter if you can. Reach out to myself or Tony or Matt after this seminar if you're interested in joining the Victorian Chapter Committee. From a personal growth point of view, it's excellent. Networking, helping inform and shape the industry. And also we're always after passionate people who, if you're here, you're usually one of those passionate people where we'd like to talk to. So get involved. And I'll hand over to Jip. Thank you.
Thanks so much, James, and welcome everybody. Thank you for giving the opportunity for me to share a bit about what it is that I do at Penske Australia around energy storage and microgrids. For those who don't know who Penske Australia is, we are the distributor of Rolls-Royce and MTU products in Australia, and have done so successfully over the years. We have roughly 1,100 employees in Australia, of which we service over 40,000 engines, and a part of that is in generators, standby backup generators for diesel as well as gas. So that is what Penske Australia traditionally does, as well as offering truck rental and truck servicing. More recently, through MTU and Rolls-Royce, we moved into batteries, and that is part of it. Why I was attracted to Penske Australia. So why have MTU, Rolls-Royce gone after batteries? Well, the energy landscape is changing quite rapidly with the rise of renewables. I got 4 slides here that indicate the change that is occurring. So on this first graph that you see here is the supply and demand of each state, randomly taken last week. where you can see all the yellow bits is large scale solar, as well as small scale solar. And traditionally, it was always brown coal or black coal, which is still quite a significant part of the energy supply, but that is rapidly changing. And because it's changing, the price of energy in the wholesale market is changing significantly as well. So what you see in this graph is you have the blue line, which is the demand during the day, and where traditionally you would have a curve that goes like this. Right now you have a major dip during the day, and that is because of solar. And what happens is that the price, which is the purple line, fluctuates between negative $1,000 per megawatt hour. So if you were to translate to cents per kilowatt hour, that is roughly $10 per kilowatt hour that you get paid to take energy from the grid at that point in time. And here you could see that it goes up to $600 per megawatt hour. Please note that this is South Australia, and which is on the forefront of all these developments. Because if you go back to this slide here, is that the majority of the supply is either solar or gas. But many days of the year, this is becoming solar and wind, and thus large fluctuations. Yesterday, I understood there was some interest as to why, especially in buildings, people are moving away from CHP plants, which Penske Australia also supplies. So gas-powered CHP, combined heat and power, and that is because of the gas price, which you can see here over the last couple of years, whereas on this axis it's dollar per gigajoule, where a couple of years ago it was relatively low, and all of a sudden in 2015, 2016, 17, it more than doubled up to roughly these figures here to roughly $8 per gigajoule, and that resulted in that those projects became uneconomical, and hence why these projects no longer stack up. On the other side here, you have the graph of what has happened with solar, and you can see that there is been steep declines of solar power. This is in US dollars, but I think where it's roughly 5 cents per kilowatt hour. But I think for rooftop solar in Australia, we are close to that figure at the moment. So all these changes in the energy environment has pushed the business case for batteries significantly, and that's where I come in. I thought I'd give a short background as to where I came from and how I arrived to this point. So in 2010, I did my master thesis on a new type of battery, which could propel this lovely electric scooter. Here you see a prototype of the battery that I built. I later on moved to a large utility/retailer organization in the Netherlands, because that's where I'm from, where I partook in the initial steps of the first large battery in Europe, realized I think in 2017 in Germany. I found Australian love and decided to move to Australia, where I joined a battery startup company called Relectrify, and they reuse battery cells from electric vehicles for energy storage. I then later on moved to another utility type organization called Enwave Australia, where they created embedded micro networks, either connecting up several buildings and trying to efficiently use large-scale solar and battery systems. You might also know Enwave from the various CHP plants that they own and operate. One that comes to mind is Central Park in Sydney, which won a large number of awards for that particular project, which is still operating. And yeah, recently moved to Penske, Australia, and this lovely picture here is of the Ausgrid battery that was in the news last week, which is one of the first community battery trials in Australia. So what is energy storage? So energy storage takes many forms, whereas a lot of times various technologies are used interchangeably. But I hope this graph gives you a little bit of an understanding of the various energy storage technologies there are on the market and are continued to be developed. So in this corner here is really your UPS type of products, where you have a system in place that will take care of your immediate power needs for a short period, and usually this is required until backup generators kick in. A technology that sort of does both is the flywheel technology, but then you would move into batteries which have a longer duration and usually a higher megawatt scale, so a higher power output, where traditionally this was led by lead acid batteries. For a large number of reasons, this is less attractive for an energy market perspective because of the low efficiencies and power limitations of those. Then you have the lithium-ion battery, which is all over the news. You have it in your phone. It's up and coming in electric vehicles, at least in Australia. It's up and coming. In Europe, it's sort of normal these days. And one thing that I thought it was interesting to point out, when people are talking about these batteries, they usually consist out of these 18650 cells, which is 18 millimeters wide and 650 centimeters long. So if you think of all these megawatt of batteries, it's thousands of these tiny batteries stacked next together in series. So it's quite an interesting feat. Another battery that I wanted to point out is a redox flow battery, which you can see an example here, which is this particular technology brand is Redflow, Australian company, and these type of batteries, they essentially store the energy inside a chemical liquid, which they then can pass through a fuel cell, which is located here via a pump. And the good thing about this type of product is that you can store it for a long time without the energy getting out of the system. And usually you can operate these systems for longer. The issue is that the cost of such a system is significantly higher than than the current lithium-ion batteries. Larger scale and more future focused would be hydrogen. At the moment, it's not really price competitive, but some significant players in the market are working on that. And you have pumped hydro, which can take a large part of energy storage requirement. An example here is in Tasmania. Pumped hydro is really good, has good efficiencies, but obviously it has limited potential applications given it requires lakes and height difference to make that happen. So that is a broad overview of energy storage technologies, but I would like to focus on the lithium-ion batteries. So these batteries are interested in a combination of factors, and one of it would be a microgrid. But what is a microgrid? So according to the definition of Rolls-Royce, a microgrid is a decentralized energy system where a combination of either renewable content or traditional generator content is applied to a grid, and an energy storage solution will help balance between these variable power loads and the consumption that is taking place by the various uses of energy. So other than the batteries, MTU, Rolls-Royce, and Penske Australia is also looking for a hydrogen solution for when it becomes commercially attractive. At the heart of this is a control system which MTU have developed as well, which is part of our solution. So I thought, yeah, at what scale do we operate? So traditionally, a power system was, you have a large coal power plant, and it would go in one line to the end user, house, offices, industrial users, and in between you have transformer steps to each time make the energy or the power output smaller and smaller, so it would be fit for use. With renewables, you have not just one generator here, but you have generation that comes in on this level, which is fluctuating, generation that comes in on this level, which is fluctuating, as well as solar panels on roofs. As you can imagine, that will create a lot of variability, and some form of stabilization is required. So you could roughly divide the market into three scales. One, you have the utility scale, which is comparable with your traditional generator. So here you see the Hornsdale Tesla battery, which is this part is 100 megawatt, and here in the back you see the extension that was done last year, which is 50 megawatt. We like to play in the 100 kilowatt to 10 megawatt hour area. Usually a single container would suffice. So the large container, which is a 40-foot container, can supply up to 2 megawatts. And this particular container is roughly 100 kilowatt to 400 kilowatts. Then on the smaller end, you have your residential / commercial batteries. Here you see a picture of the LG home battery, which I think from top of my head is roughly 10 kilowatts, 13 kilowatt hours. So a relatively small battery. But yeah, as I said, we tend to focus on this size in particular because it matches the range of our generators pretty well. As well as we think this is the target market where to date there hasn't been a lot of activity. So what can a battery do? A battery can do a lot of things, which is a good thing, but it also makes it kind of complex. So I'll try to go through each of these 6 items to give you a bit of an understanding what the battery can do. So in the first one is called energy shifting. So what that means is you absorb during the day, usually because of solar power that you have on the roof, you have excess energy, which you cannot export to the grid, or you won't get as much money for it as you would like to. And then you would discharge as soon as the sun goes down to manage that peak evening load. The second one is demand management, where you try to make your the power flows that is going into a facility, you try to manage that. So you would absorb again during the day, and then when the peak comes, your battery will kick in at a certain demand level, and then when that peak is over, it goes back into charging the battery. Spinning reserve has to do with especially microgrids for when there's either an instant significant peak and in demand, and something needs to absorb that peak. And that is called spinning reserve. It's also required for when you slowly ramp up your generator, a large generator that is, to manage the load and not have the system collapse. Then you have ramp rate control. So what you see here is fluctuations of energy production of a wind farm or a PV farm, which fluctuates all the time. And if there's a high fluctuation, that will cause additional stress to a network, and could cause the solar farms to be curtailed, so to be limited in power output because it's putting too much stress on a network, and a battery can smooth that supply of power to the grid. Then you have a voltage regulation that usually takes place on a smaller scale, on a local network scale, where due to rooftop solar, the voltage significantly increases and thus makes the local grid unstable and could damage various components there. And the battery can either supply reactive power or sort of control the voltage on that microgrid. And then the last part is called frequency regulation or frequency control. So the national grid operates at 50 hertz. And as you can imagine, when there's an increase of supply or an increase of load on the network, that 50 hertz will either increase or decrease. And it's really important for the stability of that network to have that 50 hertz stabilized, and a battery can assist in delivering power or absorbing power for short periods of time. So all these different functions can be turned into dollars, so to speak, depending on which role is being played, and its application. So a couple of case studies that MTU and Penske Australia have done to date. I thought to start off with this one. So it's energy storage to support charging. In this case, it's in Germany, and when you're charging, oh, it automatically jumps. When you're charging EVs, especially at fast charging, there will be significant stress on the local network, and which would require upgrading. But if you place a battery, you can manage that load and reduce costs for the network operator as well. A different example is Daly River in Australia, which is a microgrid in the Northern Territories, where they were traditionally being operated by diesel generators, but by placing solar and batteries, these diesel generators can be turned off during the day, and saving a significant amount of diesel, and for their energy consumptions, they can operate for 50% on renewables. Question that you might ask yourself is, why can't you go to 100? But that would require significantly more solar power, and there will always be days where the amount of solar energy is not sufficient, especially in winter, and the amount of energy storage that you would require is just uneconomical at this stage. The latest example is, as I indicated before, the Ausgrid battery. It's a community battery. What does that mean? It means that it's connected in a local community, where it will manage the voltage of that local community, and what that allows is for more solar to be put on the roofs locally, because the network won't be oversupplied. So there will be a local place where they can discharge or charge the battery, and then during evenings it can discharge. As well as this particular battery will also reduce future costs of the DNSP, which is Ausgrid in this case, future investment costs in transformers and the like. So how does a battery, as you saw just then, of what components is it made up of? So initially I spoke about the 18650 battery cell, and this is a 40-foot container, and those tiny cells are then packed in modules of, if I'm not mistaken, 250 cells, and they are then put into various racks, and these are 23 racks of battery cells connected in series, and which creates the power output required. This system needs to be managed by a BMS, a battery management system, which happens here to make sure that all these batteries are not overloaded and are not discharged at too high of rates. Then you have the inverter, which will transform the DC, the direct current batteries, into AC power or three-phase power, as most of you know, and vice versa. Or when it's charging, it will change from AC to DC. And then we have a transformer here to step it up to the required local output. This whole system is cooled on two fronts. On one front, it's inverter cooling, which does where all where most of the heat is generated, and this cooling system is water-based, so it's very efficient as a result. Just as a safety precaution, we also have an additional HVAC system, especially required when you're operating in high temperature environments, to make sure that the temperature of the batteries as well as the other electronics remain at a somewhat cool level. The key thing in our design is we have something that we call the clean room, to make sure that there's limited dust that can come in these batteries, and a dirty room or a dirt room where that is less of an issue, which is on the outside, and that makes it also easy for maintenance. So the options that we have for this product is so the container comes in a standard housing, which is classed C3M, which is suitable for most locations. But if you are in a location which is close to the sea, which is the case for the Osgrid battery, which is located close to northern beaches, C5M is required. The batteries come standardly with a fire suppression system in terms of the safety, and you can have various degrees of how much protection this system will cause. Because everything is housed in a container, relatively speaking, we have low noise emissions, where some of other battery technology or battery suppliers have some issues when it comes to noise, especially, when it comes to noise, especially the inverter part can be quite noisy. So a key feature of our battery is the microgrid controller, which will send all the required signals to either charge or discharge, as well as sending the necessary information to building management systems. The good thing about our technology in this case is that it's fairly easy to integrate with, because it has an open Modbus system. When you're looking at these batteries, one of the key issues is safety. These battery cells are on a technology that is called lithium ion. Lithium, for the chemists out there, lithium is one of the lightest metals on Earth, and one of the core characteristics of this metal is that it doesn't like to be in a pure form and loves to react with oxygen. I don't know if you guys recall high school experiments where you have sodium, pure sodium, and you add either water or oxygen to it, and it goes bang. you have the same thing with lithium cells, and I'm sure that everybody heard of your cell phone exploding and whatnot. So safety is really central focus, and hence why we have such a large strategy when it comes to these battery systems. So it starts with the cells. So for our particular technology, we use Samsung cells, which have passed the standards where they would look at what happens if you have a runaway cell, and would that if there is a fire in one of the cells, would that then cause fire in the cells adjacent to it? And in this case, our cells do not. On top of that, we have DC fuses per cell. So if there's a surcharge, it will isolate the cell and cause an overload protection. And the cell has ventilation. So part of the reason why it would explode is because water is turned into hydrogen, and hydrogen is highly flammable, and we have ceramic coating around the cell to stop the fires from spreading. So on top of that, we have on a module level, each modules are firmly isolated, and a battery management system that will make sure that all the voltage and temperature will be in the allowable bandwidth, or otherwise isolate that particular module. And then on a rack level, we have again similar management systems in place. I won't go through all of them. It might be a bit boring, but on the container level, which is more relevant. So we have smoke detectors. We also have detectors for gases, so mainly hydrogen, and if there is a fire, coal monoxide. And in worst case, we have a nozzle where you can add a water hose to for the fire department, and they can just flood the whole container with water, which will definitely stop the fire. Or we can have additional fire suppression systems using a chemical called Novec 1230, which in essence will take away all the oxygen around the cells, and killing the fire that way. So a lot of features to make sure that if there's a worst case event of a fire, that it won't damage anything outside the container, and which is quite important, especially in the build environment. I was also asked around if I could go into the regulations of these batteries per state. There is not really that much regulation on a state level, because it's a new technology. It's not really legislated as much, other than, you know, it's a electrical device, and it's connected to the energy system, which has its own sets of rules and regulations. But if you look at batteries from a government perspective, especially on state level, they really want these batteries to go in. So New South Wales, South Australia, and Victoria and Queensland all have grants that is focused around households picking up these batteries and installing them, and especially to make them VPP, virtual power plant ready. So on a household level, these loads can be managed as well as potentially provide services to the grid. And on the other side of the scales, on the utilities side of the scales, grants are the states are offering grants as well as contracts for these large-scale batteries. One example is in Victoria, in Geelong, where the Victorian state has offered a large contract to build a large-scale battery. Although that is a bit of a controversy, because there's a number of specialists in the area and consultants that have done the analysis on this particular case, and they all concluded that it will be an additional cost to the people in Victoria versus some of the other projects that are not supported by government. Yeah, as I indicated, these projects run on or need to comply with a number of standards. Two of the AS standards that you can see here, which are ever evolving. I think every year or so there's an update on these standards because of the newness of the technology. And the last one is the UL 9540A, which is a battery standard on the cell level or the module level, which tests what happens if you have a runaway cell. So they purposely make a cell cause fire and see what happens to the other cells directly around it. And Samsung, as I said before, those cells they don't ignite each other if there is a fire within one of the cells. So if you're going to connect a battery, a larger scale battery, to the grid or behind the meter, you have a number of parties involved that have something to say about that. The DNSP, the distribution network service provider, so the entity that owns all the poles and wire in a certain area, they will tell you what it needs to comply with, and you need to get approval to install such a device. If you want to be trading with the market, you need to register yourself with AEMO, the Australian Energy Monitoring Organization, and they're responsible to make sure that the balance of the energy system is maintained. And then you have your energy retailer, who, well, everybody is aware of them, which trades on the NEM, the National Energy Market, for the east coast of Australia, and their role is to trade and bill. Whereas normally you would mainly interact with your energy retailers. So I thought to dive into a little bit of a business case, and to go through the various value streams and do a little bit of an education as to what an energy bill is made up of, and yeah, understanding what an energy bill is made up of allows you to make a business case for solar initially, but also for batteries. So what are some of the value drivers for behind the meter energy storage? I think the first one is to increase the percentage of self-consumption of renewables. So if you have a solar array on a roof, and you have a surplus of that renewables, especially if you're larger than 100 kilowatts, you won't get anything back from the retailer for that energy. And a battery will allow you to use that better. But it also gives you the ability to make your solar system larger if there's space. The second thing that the battery behind the meter can do is demand shaving, as explained before. If you look at your energy bill of most businesses, you have to pay a demand charge, which can be quite significant. Next to that, you'll have an improved power quality for your facility, and thus if the power quality of the grid is fluctuating significantly, you can manage the power quality internally, and that will cause your machinery to operate for a longer life. And in some cases, depending on the business, you can decrease the power connection to the grid in combination with solar. This is very dependent on how energy is used for a particular business, but it can be a significant cost saving. Then you can have a battery still behind the meter, but interacting with the grid. So it will become a virtual power plant. And then you could trade on the wholesale market on the NEM, which is called arbitrage. So you charge the battery when there's a really low price or a negative price. So you get money for absorbing energy, and you sell the energy when there's a really high price in the market. Then there's something that is called FCAS, which is something that you sell to AEMO to help them balance their energy system. FCAS is short for Frequency Control Ancillary Services, and there are 11 markets that you could supply to, and this particular market is the main target for the large-scale batteries, and that is how, for example, the Hornsdale battery made a very significant amount of money 2 years ago, because it was the first battery to come in and could soak up a big piece of the pie. If you're wondering how that comes back into your bill, here you see market charges. So these are charges that AEMO is charging everybody, and this is the ancillary services that everybody's paid. Everybody who is connected to the grid is paying for. It seems like a very low cost, but the whole system is quite significant, and it quickly adds up to hundreds of millions of dollars. And this is a fee for the AEMO to operate. You could also do a peer-to-peer trading. So if you have a neighbor that has solar, and another neighbor has a battery, you could make a deal together via a special company that sits in between, or a retailer that allows you to say, okay, I have surplus energy, I will charge the battery of my neighbor, and when the sun is down, that battery will give me energy for less than what then I have to pay to my energy retailer, as an example. Then you can offer services to the DNSP. So the voltage control is an example of that, which is one of the big features of the Osgrid battery. And then you have something which is called the RERT, reliable and emergency reserve trading. So in cases when there is a blackout event, or when there's significant reduced supply available, so there's a failure at a coal power plant, then this kicks in to make sure that there's enough supply to prevent a blackout from happening. So what does that mean? What can you do on a behind the meter level? So again, you can, if you have an embedded network, yeah, we sort of touched on this already, focus more on demand management. What are the things that you can look out for in buildings, especially high-rise buildings with elevators? They have very peaky demand, and if the building is charged on peak demand, a battery might be a very interesting business case, because overall buildings have a very, relatively speaking, a low energy consumption, and the same thing goes for cooling. That if you have, for example, a large residential building, everybody comes home at 6 in summer, and everybody turns on the air conditioning. That initial peak might be able to be managed by battery, and again power quality, and you can turn the battery into a VPP as discussed before. So if we do a simple business case, first focusing on the energy bill. So I'm just going to walk through each item at the minute. So you have consumable charges, fixed charges, and demand charges. Whereas consumables, you're probably most familiar with. You have your peak and off-peak, which is a variable rate depending on how much energy you consume. This goes up. So you have your peak and off-peak. Then you have your market charges, which is a small figure, but again, a cent per kilowatt hour. Then you have your metering charges and your retail charges, which is a fixed fee for providing that service to you. Then you have your environmental charges. These charges are paid for the renewable grants offered by the government. So if you have a solar system on your roof for less than 100 kilowatts, you get an upfront grant from the government, which is being paid by everybody, which is this figure here. Then you have for Victoria a special charge, which is the Victoria Energy Efficiency. Not sure what the T stands for, but it's for example, if you change over your factory from your lights to LED lights, becoming significantly more efficient, the Victorian government is offering you a grant for that, and everybody's paying for that. And then you have your large renewable energy target, T target, yeah, which is an ongoing fee. And the SRES and the LRET, they're tied into the National Energy Renewable Energy Target, which comes to an end at 2030. And then you have your network charges of the DNSP, again, a fixed charge for their service. Then you have a consumable rate of which they charge for how much energy you use. And then you have the demand charge, which is the amount of power that you consume during a peak moment. Now, if we want to make a business case, then I've added up all the consumable peak charge rates. So there's 11 cents, these components, and the 4.3, making 19.1 cents per kilowatt hour, or $191 per megawatt hour. And the second thing that we can influence is the demand charge. So assuming that 156 is occurs during peak hours, we could influence that with a battery and solar. So annually, the 155 kVA comes down to roughly 17K per annum. So say we add a 100 kVA battery or 100 kilowatt battery. This is a rough estimate of what the capital cost would be for such a battery, making it $150,000 cost to install a battery for this location. Say we have solar on the roof and we would add additional solar. I'm quite confident that you can get power from that solar panel for $100 per megawatt hour. So if we subtract this figure with this figure, this would be the saving that you could achieve compared to the peak energy cost. And if you multiply that by daily figure by 365, we come to $33.2 thousand per annum that you could save on your energy bill there. And if we assume that we can take off 100% of the battery of this 155, meaning that you would only have a demand charge instead of 56 kVA, it will reduce to 56 kVA. Then you have a saving of an additional $11,000 per year. And if you would just do a simple add these two, which would make it $44,000 a year, and you divide the capital cost through that annual savings, you would have a simple payback of 3.4 years, which for most businesses are quite attractive. So what's next? So this example that I gave initially for South Australia, which was yesterday, the price, this is likely going to occur for Victoria, New South Wales, Queensland, not so much Tasmania, because they have a large amount of energy storage through their hydro assets there. But you can quite clearly see, as more renewables come into the system, the daily demand on a state level will get lower and lower and lower, which will have significant impacts on the price, turning from positive to negative, and vice versa, and thus more batteries will become more appealing to businesses. Another big trend that is happening is the decline of cost of batteries. Just like solar the battery price, which is currently sitting somewhere here for large scale solar, for large scale batteries. Installation cost is quite a bit higher because of the number of additional components that is required. But it sits somewhere here, so it and it's projected to go half the next couple of years. I think this again, just like solar, this will even accelerate even more. Whereas I think within 3 to 4 years, you already be at this $200 per kilowatt hour installation cost. One thing that is a bit of an unknown at this stage is what is happening as we ramp up is going to happen to the supply chain of lithium. So there's only a handful of lithium mines in the world, and which are currently coping, but the majority of the lithium packs will go into EVs, which might cause some constraints in terms of reducing these packs on the long run. But what is going to happen in my mind is you're going to have multiple battery technologies. So as I discussed before, you have the redox flow batteries with different cell chemistries, so zinc bromide, vanadium, iron bromide, as well as other metal air batteries. As an example, the battery that I was working on as a student was a zinc air battery. And the good thing about zinc is that it's really cheap piece of metal compared to lithium to make for a number of reasons, and thus the cost price of such a system can become really low and will be useful for different applications. So there will be a change in batteries, multiple different battery technologies. A different thing that is already occurring is the virtual power plants, but also community-based grids. So we're completely moving away from this this traditional energy system where you have a large coal plant or a large gas plant, which produces a lot of energy on one spot and then transports that energy to the various end users, where with these virtual power plants and community-based grids, everything will be distributed and local, and trading will likely occur on a local basis and can potentially cut off parts of the larger systems and reduce costs that way. Another upcoming concept in Europe and the US is vehicle to grid. So you have an EV that is connected to the grid, which could just like a standard battery, if you have these low prices, charge when the price is really attractive, and then if there is a peak demand during the day, that these vehicles could use their battery to charge or to discharge during that event. I myself am a bit skeptical around this concept because when you have a vehicle, you want to make sure that it's charged and ready to go for whenever you want. say you get this figure here, which is, say, it is $10 per kilowatt, and that's a fee that you would get. Would it be worth, say, $20-$30 for you to be dependent on that moment in time, or would you want to have, you know, full control over when you want to charge a battery and when you want to take it for a drive? Another big step that is currently occurring, and some big projects are being planned as we speak, is around hydrogen, and it's mainly a different way of looking at it. Is it's going to be renewable energy export. So you have these large solar farms and large wind farms in Australia, where there's a lot of resource and a lot of land available to build these systems, whereas in case of Japan and Singapore, that is not the case. So in Japan, they're changing some of their power infrastructure to be able to use hydrogen as a fuel source, whereas there's a project called Sun Cable that contemplates building a power cable from Western Australia to Singapore, providing renewable energy to them. There's a lot of plans to push the energy production of renewable energy in Australia to 200, 400, 500% of its own energy needs, and those countries would really like to see that happen. And yeah, the big question is that then the end of fossil fuel powered energy? And that is a question that, especially at Penske, who is really focused on being really good at providing diesel backup power generation and prime diesel power generation, with all these mega trends, is that going to be the end? And what's next for us? Yeah, thank you for listening, and hope it was interesting.
I'll now, thanks for that, Jip. Thanks, and I'll just now open up the floor to some questions. There is one. Jip, great presentation so far. In terms of your MTU battery systems, can they be safely installed indoors, say underground or inside buildings? Yep. So yeah, I don't see why not. They've passed a number of tests. Just thinking if we actually place it inside a building before. I don't think we have done that before, but we are planning to do so with one of our customers. Yeah. I'd like to ask a question of my own. Do you see many privateers coming into the market and asking, like the likes of transportation companies or small manufacturing businesses? Just to, I was thinking, like from an AG Coombs point of view, we do a lot of welding and fabrication. Do you see that demand yet in the market? Have you had much call for that in the market in terms of the manufacturing sector asking for battery to take out those peaks, and they're installing, say, up to 100 kilowatt solar on their roof? Have you seen much market demand for that yet? Not that much, simply because so the capital cost that I showed you in that slide
is going to occur, by my estimate, by the end of the year. And because at the moment it's still a bit higher, the economics doesn't really stack up as of yet. But I'm pretty sure that that will change in the near future. So other business cases for batteries are more attractive at this stage, which you work on.
The other question I have is, this is another question from me, but I'll open up the floor to others. Do you see what you're providing as an alternative to, say, centralised UPS systems for the building sector? Like, can they work in the same manner, but, you know, being at the grid supply level rather than the internal level?
In theory, you could, but because you are actively using these batteries, you're not 100% sure when you have your battery which is fully discharged, and if there's no charge, you know, the UPS is not really useful. Yeah, so you will, yeah. You're muted there, James.
About to read out another one for you. Would there be standards dictating ventilation requirements of the above? That's on the back end of the question about internalised building storage or storage of batteries internally. Yeah,
no, 100%, because the HVAC requires a minimum airflow. So yeah, that's my expectation, that there is a requirement for minimum amount of airflow to make sure that the HVAC system can operate sufficiently. Oh,
unmute.
Yeah.
Just if there's any more questions, I'll put it out there. Otherwise, we'll wrap up and let everyone get off for the night. But I found it informative, and thank you for attending, Jip, and giving us your time tonight. If there's any questions, I'm sure you can reach out to Jip directly. From those who have attended, I'd like to thank you for all attending tonight. Hopefully you've learned something. It's a hopeful environment we're moving into. I think it's a good thing for change. Maybe your power systems will be our generation systems of hospitals in the future, maybe, I don't know. But certainly I can see what you mean by CHPs. I don't think many people will be putting in CHPs in the future moving forward.
Yeah, so part of the reason why the price got pushed up is because we started exporting to the world, and that wasn't a really good thing for us in Australia.
Okay, I'll let everyone sign off. Thank you for everyone turning up to tonight's CIBSE presentation. Thank you, Jip, again. And that's my son in the background about to read Peter Rabbit. But thanks, everyone. Cheers.
Thanks, guys.